Hello, good evening. Salma, are you there? Hello, everyone. Good evening. Good evening, everyone.
Good evening,
Please,
sir.
okay, good evening. Confirm that you can hear me and hear me very clearly.
Confirm, sir.
Okay. Thank you and welcome to today's facilitation. This is our third week. CHM1 organic chemistry. So far, we have been trying to look at organic compound. Started with hybridization, covalent ionic, and then from there we moved on to look at how organic compounds could be classified based on atom or group of atoms, otherwise referred to as a functional group. And then we looked at that functional group, considered quite a lot of them, the alkanes, the alkenes, the alkynes, the carboxylic acids, the alcohols, the amines, the amides, the esters, the ethers, and the rest. And so today we are continuing this facilitation looking at nomenclature. So what we have today is nomenclature. Nomenclature simply means name. So we want to learn how compounds, particularly organic compounds, appear, how to decide what is what, and why is this named this way, why not the other way. So let us begin by looking at history. Earliest attempts to name organic compounds were based either on their origin or on their properties. So you now name compounds based on where it is obtained from or based on how it behaves. And that led us to what we have as citric acid. When you hear citric acid, it's just a common name for organic acid obtained from citrus fruits. So, and then there comes a problem. Number one, what if compounds, there are more than one acid found in citrus fruits? What are we going to name them? Since the name is based on the origin and both of them have the same origin, how are you going to name them? So it's a problem. Then there is this other way of naming compounds based on character, how they behave. And that introduced compounds called aromatic compounds. These compounds were formerly referred to compounds that have aroma or sweet fragrance. So because the compounds have very sweet fragrance, which means aroma in Greek, those compounds were classified as aromatic compounds. And now there comes a problem too. All aromatic compounds coming from all aromatic compounds with sweet fragrance. And so these were actually how compounds were named originally, either their origin, like I mentioned, you have citric acid coming from citrus, or from their characteristics, where you have aromatic compounds having aroma or fragrance. So from there, let us quickly look at one thing also that will help us form the problem. why the normal naming of compounds cannot stand the test of time. Isomerism. Isomerism is the term used to describe the exact or different structural formula. So when I is referring to the fact that these compounds have the same molecular formula, but different structural formula. We have a typical example here, which is C4H10. C4H10 is a typical alkane, and it can be arranged in two different ways. That is to say, it has two isomers. Number one is butane. Number one is butane. You can see this. Each of the points here represents carbon. And you remember carbon is tetravalent. So for every carbon, there must be 4 bonds around every carbon for it to be a stable carbon. So if you look at the carbon here, there are 1 carbon to carbon bond, then there will be H3. So this point at the edge here is a CH3, then this point is a CH2, this point is a CH2, and then this point is another CH3. So if you count them, you see there are 1, 2, 3, 4 carbon atoms in this compound. And then there are how many hydrogens? Let us count it. We have 3 here, 4, 5, 6, 7, 8, 9, 10. So there are 10 hydrogens here. So, and that makes this compound butane a normal a member of the C4H10 family. And now, let us now look at this particular compound here. At this edge, center here is a carbon. And like we said, carbon has to be tetravalent, 4 bonds. So, but if you look at the bonds, somebody is saying she or he cannot see the screen. Are there other people who can see the screen?
Yes, sir.
Okay. So, Ruth, how do we help you now? You can hear us, but you cannot see the screen. Is that the problem? Is that the case?
Yes, sir. Yes, sir.
You can hear us, but you cannot see the screen.
Yes, sir.
Ah, this case is critical. How do we? Okay, do you know what you can do? Was there any point you were seeing the screen at all?
Not at all.
Oh. Can you log out and log in again?
Okay, let me try that.
Please try that. Let's see if it will solve your problem. Okay. So while waiting for Ruth to join, we have to continue. So if you look at this, there is a carbon here, but instead of CH2, you can see there are already 3 bonds surrounding this carbon, so there will only be 1 hydrogen. Then the carbons at these points are having CH3, CH3, CH3. So 1, 2, 3, 4, 4 carbons. Let's look at the hydrogen, 3 here, 3 here, and 3 here. That is 9 plus the 1 here, that makes it 10. So these 2 compounds are said to be isomers. They are said to be isomers. I think Ruth is back. Ruth, are you back?
Yes, sir, I'm back. I can't see the screen. No, it's just in
the the screen is still. It's
yes.
just what? What are you seeing? What are you
It's just
seeing?
blank. David Ugwu has started screen sharing. Then just your video and the screen is black.
What will be the problem? Okay, let me reshare.
Okay.
Let me reshare the screen whether
Okay. I can see it now.
you can see it now. Okay.
Thank you very much.
All right. So as I was saying, okay. As I was saying, so you can see that butane and 2-methylpropane are isomers. If we use the naming that comes from the origin, how are we going to account for 2-methylpropane, which is an isomer of butane? Possibly two of them will occur in the same place. So how are we going to account for it? And therefore, the normal naming or the common names comes with serious ambiguity. It comes with serious ambiguity. You cannot exclusively name a compound and that name belongs to that compound alone using the old naming method, where the compound is named because of its origin or because of its characteristic. So we now just to further look at isomerism, we decided to go a step higher, where we are considering carbon number 5. So if we have C5H12, which is normally pentane, we want to look at the isomers of pentane. So you can see all of them, we have 5 carbons. We have 1, 2, 3, 4, 5. 5 carbons. 1, 2, 3, 4, 5. 5 carbons. 1, 2, 3, 4, 5. 4, 5. 5 carbons. All of them have 5 carbons, right? And then let us confirm also that all of them has 12 hydrogens. The edge has 3, which is 6, 7, 8, 9, 10, 11, 12. So this one is confirmed to have a C5H12. Then here we have 3, 3, 3, which is 9, 10, 11, 12. So still another 12. Here we have 3, 3, 3, 3. There is no hydrogen here because carbon is tetravalent. And if you look at this carbon here, you can see that it's already having 4 other bonds. So there is no way there will be a hydrogen. So you see 1, 2, 3, 4. So this carbon here has attained its tetravalency. And because it has attained its tetravalency, there is no point having an extra hydrogen. It cannot accommodate more. So you now see that C5H12 has 3 isomers. Number 1 is pentane, which if you follow the normal, the common name, they will say normal pentane. Normal pentane to show that there is no branching. And then we have another one, which is 2-methylbutane. 2-methylbutane. Don't worry about these names. We are going to look exclusively at nomenclature today. So at the end of our meeting today, you should be able to pick any organic compound and name them without ambiguity. Then we have the other one, which is 2,2-dimethylpropane. But the important thing is that 3 of them are isomers of pentane because all of them has 5 carbon and 12 hydrogen. So number of isomers in a molecule, we have this table. So when you have 4 carbons, we have 2 isomers. Below 4, there is no isomerism. So carbon number 3, 2, and 1 does not exhibit isomerism. So carbon number 5, 3 isomers. Carbon number 6, 5 isomers. You now observe that as the number of carbons 4 was just 2, 5, 3, 6, 5, 7 carbons, 9 isomers, 8 carbons, 18 isomers, 9 carbons, 35 isomers, 10 carbons, 75 isomers, and so on. You can see that just 20 carbons will have 366,319 isomers for just 20 carbons. So the question now is, if we resort to using the origin of the organic compound as a way of naming the compound, or we resort to the characteristics as a way of naming the compound, then how are we going to be able to learn and understand the whole of this? We are still between carbon number 4 and 20, when we're already having over 4, close to 370, more than 370 compounds, more than 370,000 compounds. So there now come what is called International Union of Pure and Applied Chemistry, IUPAC. IUPAC simplified the naming such that compounds will no longer be named based on their origin, and then compounds will no longer be named based on the characteristics. Rather, compounds will now be named based on the functional groups present. So with IUPAC nomenclature, we recognize the functional group present, and that will form a way of naming the compound. And what that simply means is that once you learn the rules, irrespective of how big or small the compound is, you only apply the rules for naming, and then you will be able to arrive at the correct name of the compound without ambiguity. So most organic compounds are derivatives of alkane. If you remember when we were looking at functional groups, you remember alkyl group, and you will see that in alkanol and the rest of other compounds, they all contain an alkyl group, which is derived from an alkane. Okay, so what that simply means is that if we learn how to name an alkane very well, then we have solved our problem with naming other compounds of varying functional groups. So learning the nomenclature of alkane is fundamental to learning the nomenclature of other functional groups, very fundamental. So alkanes generally are known by their formula CnH2n plus 2. This is the formula for every alkane. Take note that these particular alkanes with CnH2n plus 2 must be acyclic. If you remember the other time when we were classifying compounds as hydrocarbons and then non-hydrocarbons, you remember under hydrocarbon, we had the aliphatic and the aromatic, and then under aliphatic, we have the acyclic and the cyclic. Okay? So, for you to use the general formula of CnH2n plus 2, the compound must not be a cyclic compound. For cyclic alkane or cycloalkanes, their general formula is CnH2n. So for you to use CnH2n plus 2, those compounds must not be cyclic. And then where n is an integer, that is to say n cannot go for a fraction. N must be a whole number. Of course, not 0, not greater than 0, because if it's 0, that means there is no carbon. And if there is no carbon, then you cannot be talking of organic compounds. So the first 4 alkanes retained their original or non-systematic names. That is the common names coming from their origin, where they originated from. The names coming from where they originated from were retained in the first 4 alkanes. However, the Greek name or the Greek word was now used as a prefix As soon as we go above carbon number 4, we now apply Greek word to determine the number of carbons present. So the name of alkanes higher than this start with a prefix, okay, which indicates the number of carbon atom in the chain. And then it ends with a suffix, ane, ane. And that is what makes it an alkane. If it is not an alkane, if it is an alkene, it is going to end with the suffix ene. Okay, so it is from this last word that you know the functional group present in a molecule. So we have these compounds here. This is our table. And this table, you see here, we have CH4, 1 carbon, 4 hydrogen. And this is for N equal to 1. If you substitute, go back, we said CnH2n plus 2. If we substitute N for 1, we have C1, H2 multiplied by 1 is 2, 2 plus 2 is 4. So when N equal to 1, we have CH4. And when N equal to 2, we have C, N is 2 now, so C2, H2 multiplied by 2 is 4, 4 plus 2 is 6. So we have C2H6. If N is 3, we have C3, H2 multiplied by 3 is 6, 6 plus 2 is 8. So you now have C3H8. When N is equal to 4, if N is 4, we have C4, H2 multiplied by 4 is 8 plus 2, which is 10. If you have followed what I am saying, you will recognize that there is an incremental CH2 as you move. So let us come back to our table. I was only trying to use those ones to show you how what we have in the table were generated using the formula we already discussed as the general formula for alkanes. So we have C is equal to 1. We have CH3 or C2H6, where N equal to 2. Where N equal to 3, we have CH3, CH2, CH3, which is C3H8, where now so sorry for the network break. So as I was saying, immediately after carbon number 4, the compounds of 4 carbon, we now apply the Greek word. In Greek word, pent means 5, hex means 6, hept 7, oct 8, non, and 9, and then dec 10. So when you have pentane, okay, that is 5 carbon. Then hexane, you remember a pentagon. Pentagon has 5 sides, hexagon has 6 sides, heptagon has 7 sides, octagon 8 sides, and so on. So you relate it to what we are saying here, and you see that pentane, it will have 5 carbon, then hexane 6 carbon, heptane 7, octane 8, nonane 9, decane 10. Then if we move away from just the simple 1 to 10, we are going to have the undecane, which is 11, dodecane, which is 12, tridecane, which is 13, tetradecane, which is 14, pentadecane, which is 15, hexadecane, heptadecane, okay, octadecane, until we now get to icosane. Icosane is carbon number 20. Triacantane is carbon number 30. Tetracantane is carbon number 40. Pentacantane is carbon number 50. And then hectane is carbon number 100. So what you are going to do immediately is you will use the number here, which is N. You go back to our formula, which is CnH2n plus 2 for an alkane. You go back substitute for carbon number 7 when n equal to 7. What will it give you? What will you have? So branch chain alkanes are named following certain rules. There are rules that we must observe before we can arrive at the name of a branch chain alkane. Rule number 1, the longest continuous chain of carbon atoms is taken as the parent hydrocarbon. Longest continuous has nothing to do with being a straight chain. So let us together look at what we have here. We can see there are branches. We have 1, 2, 3, 4, 5, 6. If we name number from here, we have 6, which means this compound will be a hexane. If we number from here, we have 1, 2, 3, 4, 5. 6 is more than 5. Remember, the rule said the longest continuous chain. So when we followed from here, we had 1, 2, 3, 4, 5, 6. When we followed from here, we had 1, 2, 3, 4, 5. Now let us look from here. We have 1, 2, 5, 6, 7. Is there any other way we can get something longer than 7? Let us check. 1, 2, 3, 4. No. 1, 2, 3, 4, 5. No. So you can see that the pattern that is colored red has the longest carbon chain. Let us go back to our table. When we have 7, when n is equal to 7, what do we have? Heptane. So the parent name for that compound is heptane. But unlike what we had in the table, where we have just simple compounds. You can see that outside this red colored carbon chains, there are other carbons that are on black color, right? You can see there are 2 other carbons. And that is to tell you that the name is not just simple heptane. We must give it such a name to account for the branched chain carbons. Those carbons are the branches. We must give it a name so as to account for them. However, the first rule said we must give the parent hydrocarbon to the longest continuous chain of carbon atom, longest. So, and that is why here we have arrived at 7 being the longest, and we are definitely giving the parent name to this compound as heptane. Now, let us look at rule number 2. Identify the substituent groups attached to the parent chain. Okay, we must identify the substituent group attached to the parent chain. Last week, I think last week, we were looking at alkyl groups, and we made mention of methyl group, ethyl group, propyl group, and so on. Now, if a group is attached to the longest carbon chain, the longest continuous chain, we must account for that group that is attached. Let us go back to the structure we considered earlier. You can see there are 2 methyl groups. This is a methyl group. This is also another methyl group. And these 2 methyl groups will be accounted for as a substituent. And that is what rule number 2 is saying, that we must identify the substituent groups attached to the parent chain. For this one, the substituent groups are methyl groups, 2 methyl groups. Those substituents could be ethyl, they could be propyl, they could be butyl, they could be any of these, or even the ones that we have not covered in this table. So rule number 3, the parent carbon chain is then numbered. So you must number the parent carbon chain in such a way that the substituents get the lowest possible numbers. We are going to use these 2 examples to demonstrate. We are going to use these 2 examples to demonstrate. It was covering something, so I had to. We are going to use these 2 examples to demonstrate. First of all, I want us to identify the longest carbon chain. If we follow from here, we have 1, 2, 3, 4, 5, 6. This is 6 if we follow the straight chain. Let us take another route. 1, 2, 3, 4, 5, 6, 7. So the longest carbon chain is obviously going to be, okay, let's check other variables. 1, 2, 3, 4, 5. So obviously the longest carbon chain is going to be 7. Okay, the longest carbon chain is going to be 7. And if the longest carbon chain is 7, that means the parent hydrocarbon here is a heptane. Heptane. Okay, so the rule number 3 which we want to apply is that the rule number 3 says that we must number the parent carbon chain in such a way that the substituents get the lowest possible numbers. So we are going to, you see, these 2 are the same compounds. The only thing different is in the numbering. So we want to look at the 2 numbering and then identify the position of the substituents. So if we number from here, you can see the first methyl group is at position 4. You can see 4 here. Then the second methyl group is at position 5. So 4 plus 5 is 9. Then let us go from here and see. If we number from here, 1, 2, 3, 4, 5, 6, 7. So it's still the same heptane. However, if we look at the substituents here, The first methyl group is at position 3. The second methyl group is at position 4. So 3 plus 4 is 7. Remember, this one was 4 plus 5, which is 9. So which one is lower? Of course, 7 is lower than 9. Therefore, the correct numbering for this compound must start from here, not from this place. If you start from this place, this compound is going to be 4,5-dimethyl, which is wrong. If we start from here, this compound will be 3,4-dimethyl, which is the correct system of numbering. So rule number 3 must be obeyed. And that rule says that the substituent must be numbered in such a way that they get the lowest possible numbers. Now, let us go to rule number 4. Prefixes like di means 2, tri means 3, tetra means 4, penta means 5, hexa means 6, hepta means 7, and so on. Prefixes like di, tri, tetra, and so on are used to indicate 2 for di, 3 for tri, 4 for tetra, and then 5 for penta. Similar substituents, respectively. What does that mean? If the substituents are 2 and they are the same, like we have here, you can see the substituents are 2 and both of them are methyl. The substituents are 2, both of them are methyl, which means they are the same. Therefore, we are not going to say methyl-methyl. Rather, we can use dimethyl. Di means 2. Methyl there now shows we have 2 methyl. We can use trimethyl if they were 3. Diethyl, triethyl, tetraethyl, and so on. That's rule number 4. Then rule number 5, the name of the compound is obtained by writing the location, that is the position and name of the substituents, followed by the name of the parent alkane. The position of the substituents, the name of the substituents, then followed by the name of the parent alkane. So if we are going to write the name of this one, remember we said this numbering is wrong, so the correct numbering is this one. So if we are going to write the name of this compound, we start from 1, 2, of course, we have agreed that the parent is heptane. And then there are 2 methyl groups, 1 at position 3, 2 at position 4. So the name of this compound, we say, first of all, we must indicate the number. Okay, that is the position. So this compound, first of all, you have 3, 4 dimethyl, which is the name of the substituent, then followed by the name of the parent alkane, which is heptane. So that means that this compound is going to be 3,4-dimethyl heptane. 3,4-dimethyl heptane. Rule number 6. When more than one type of substituent are present, you know, the last one we consider, we only had a methyl. What if we have both methyl, propyl, ethyl? In one compound, what do we do? And that is what rule number 6 wants to solve. Then they are cited in. For us to understand what we mean by alphabetical order, let us go back to our table. This is our table. This is methyl. Methyl started with M. This is ethyl. Ethyl started with E. This is propyl. This one is not part of the name. This is propyl started with P. This is butyl. Butyl started with B. So if we have the whole of this as substituents in a molecule, we will arrange them in alphabetical order. The first one here is E comes before others now. Counting your A, B, C, D. it is first of all B, which is butyl. B comes before E. It is after B that you have E. Then after E, you have M. If after M, you have P. So whether the P is number one, whether it is 1 propyl or 2 propyl, it is not part of the consideration. What is important is that you must number them, you must write them alphabetically. And in this alphabetical order, the prefixes are not part of it. You don't use di, tri, tetra to decide the alphabetical order. So what you use is the name of the substituents: methyl, ethyl, propyl, butyl, pentyl. These are the names that you use, not whether it is diethyl. You now say it started with T. No. Okay. So I want us to look at this compound here. First of all, let us identify the longest carbon chain. We start here: 1, 2, 3, 4, 5, 6, 7, 8. Let us look at the other possibilities: 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So the longest chain is 8, which means the parent's name is octane. The parent name is octane. Then we want to look at the substituent. The second thing is, are there substituents? Yes. You can see one substituent here. You can see the other substituent here. The third thing is to identify the position of the substituents. We start here: 1, 2, 3, 4. So we see there is a methyl group at position 3, and then there is an ethyl group at position 4. So 3 plus 4 is 7. Let us see 3, 4, 5, 6. Okay, so 5, 6. So this one will now give us 5 and 6. And 5 and 6, 5 plus 6 is 10. So 3, 4 is better, is lower than 5, 6. Therefore, the correct name or numbering for the substituent must be 3, 4, not 5, 6. Okay, now that we have identified these two, let us look at the nature of the substituent. At position 3, we have a methyl group. At position 4, we have an ethyl group. So between M and E, which one comes first? E. Therefore, the name of this compound is 4-ethyl 3-methyl octane, not 3-methyl 4, not 3-methyl 4-ethyl octane. No, it has to be 4-ethyl because E comes before M. Good. Let us again take a look at another example, which we have here. The other example which we have here, the first assignment is usually to identify the longest carbon chain: 1, 2, 3, 4, 5, 6, 7, 8, 9. So, which means this compound is going to be a non-name. And then we have, let us number from here: 1, 2, 3, 4. We also have another one at 5. So 4 plus 5 is 4 plus 5 plus 5, because there are 2 substitutes: 3, 4, 5, 6. So 5 plus 5 is 10, plus 6 is 16. So 14 is lower than 16. Therefore, the correct sequence is this way. So in this, you can see that here we have a substituent with a branch. So we are going to write 4. We now put brackets 1, 1-methyl ethyl 5,5 this is L, not 1. Okay, so we are going to have 4 brackets open because of this branch. 1-methyl ethyl 5,5 because there are 2 methyl groups here. So, and both of them are at 5 position. So we have 5,5 dimethyl nonane. Rule number 8, classification of alkyl groups. Alkyl group could be classified as primary alkyl, secondary alkyl, or tertiary alkyl. In primary alkyl, there are 2 hydrogens. In secondary alkyl, you have only 1 hydrogen. In tertiary alkyl, there is no hydrogen attached to the carbon. Rule number 9. When more than 1 carbon chain of equal length are available, like you have 2 varieties where both of them are given the same carbon chain length. The numbering is done considering the following points. 1, the principal chain should have all the chains that should be favored. We number 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So you see, if we go like this, we have 8 carbons. If we go straight, we have 8 carbons. But rule number 9 says we must give that one that will give more substituents. So let us take a look at them. If we go from here, that is this way. How many substituents are we going to have? 1, 2, 3, 4. So if we go from here, how many substituents are we going to have? 1, 2, 3. Therefore, the correct name for this compound must be such that 1, 2, 3, 4 will be pointed out as substituents. The next thing we need to do is to quickly look at the numbering, whether from this position to this position, it will give us the list. We already know how to do that. So we have 2, 1, 2, 3, 4, 5, 6, 7, 8. So we have methyl at 2, ethyl at 3, that is 2 plus 3, 5. There is another methyl here at 5, which is 10, 1 at 6, which is now 16. So if we number from here, we have 16. Then let us see what we have if we number from this side. We have 1, 2, 3. 3 plus 4 is 7. 7 plus 6 is 13. 13 plus 7 is 20. So remember, we all agreed that the least will be the most favored. So the correct numbering will follow this line so that we have 2, 5, 6 trimethyl. Then ethyl group is at position 3. And you now apply the rule of alphabetical order. So if you apply the rule of alphabetical order, you know that E comes before M. Therefore, the correct name will be 3-ethyl, 2 for this, 5 for this, 6 for this. Try to show that there are 3 methyl, trimethyl octane. That is the correct name. Then we look at this other one again, and then these two are the same. They are the same compound. So don't think they are different. They are the same compound. So here we have 1, 2, 3, 4, 5, 6. Let us take again 1, 2, 3, 4, 5, 6. Let us take again 1, 2, 3, 4, 5, 6. So what it simply means is that the longest continuous carbon chain in this compound is 6 carbon, which is hexane. The next rule to look out for now is that there are varieties given the same number of continuous carbon chain. So we must first of all identify that longest carbon chain that will give us more substituents. Okay. So we go from 5, 6. We have one substituent here, the second one here, and then the third one here. 3 substituents. If we go from here, 1, 2, 3, 2, 4, 5, 6. That is 3, 4, 5, 6. We have 1, 2. We are going to have substituents, and that is the correct numbering. That is the correct numbering. Applying rule number. If we have a 1, 2, 3, 4, 5, 6. So we have a methyl group at 2 position, and then another methyl group at 5 position. We have an ethyl group at okay. So as I was saying, so applying rule number 9, the correct name for this compound will now be 2, of course, E comes before M. So we have 3,4-diethyl, 2,5-dimethyl hexane, and that's the name. So nomenclature of other compounds, in case we have alkene, that is where there is carbon-to-carbon double bond. The ANE ending, of alkane is replaced with ENE. The functional group here is C-to-C double bond. And in numbering, for wherever there is a functional group, you must number in such a way to give the functional group the least number. The functional group must have the least number, not the substituent this time around, rather the functional group. In alkane, you are looking at only the substituents, because in alkane, all of them have sigma bonds. They are all sp3 hybridized, so there is no specific functional group. But in alkene and others, you must identify the functional group and give it the least numbering before you consider the substituents. So ANE of alkane is replaced with ENE, and that is the functional group. You give it the lowest numbering. So this is ethene, this is propene, and then here we have put 1 in. Why do we have but 1 in? Take a look at this second one. These 2, or rather these 3, are isomers. And that is why the position, as soon as you move away from carbon number 3 for alkene, you must identify the position of the double bond. Remember, we say the double bond is the functional group, and they must be given the least number. So we can't start from here if you put 3 in. No, we have to start from here so that the double bond will now receive the least numbering, which is 1, and therefore This is but one in. Then if we move from here 1, 2, but 2, if you move from here 1, 2, but 2, so wherever you start, it is the same thing for this particular one. Then this is a 2-methyl propene. You see, propene is 1, 2, 3, and there is a methyl group at position 2. Then the same thing goes for alkyne. Alkyne is known with the carbon-to-carbon triple bond. That is the functional group. The Ne of alkane is replaced with YNE. So instead of alkane, this becomes alkyne. YNE, ANEN. So the functional group is carbon-to-carbon triple bond. So this is ethyne. This is propyne. This is but-1-ine. This is but-2-ine. Now, let us take a look at this structure. You see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the important thing is that this compound is a pentyne. Now, to remember the rule, which is very important for where there is functional group, if we were to avoid that rule, remember, if we follow here 1, 2, this methyl group will be at position 2. But this alkyne, the carbon-to-carbon triple bond will be at position 3. However, if we come from here, the carbon-to-carbon triple bond will be at 1, 2, position 2, while the methyl group will be at position 4. We are disregarding the position. Remember, the other one, we give this one 2. But because of this alkyne group, which is the functional group, we must follow this pattern. Because that one we give this alkyne 2, while this one we give it 3, and 2 is lower than 3. And remember I mentioned that the functional group must receive the least number. So that makes this to be 1, 2, 3, 4, 5. And the methyl group will now be at position 4. And the name will be 4-methyl-pent-2-ine. The same thing goes for alkyl halides. The same thing goes for alkyl halide. This is bromo. 2-bromo-butane is 4. This is 2-chloro-5-methyl-hexane. Why chloro first? Because C comes before M. We already mentioned it. Then this is 5-bromo, 1-chloro, 2-iodo, 4-methyl-pentane. Why this arrangement? Because bromo, P comes before C, C comes before I comes before M. And so it must be arranged in this order, not any other order. So what do you do? First thing you do is to identify the longest chain, which is 1, 2, 3, 4, 5. Then you now look at the functional groups. We have chloro at position 1, iodo at position 2, methyl at position 4, bromo at position 5. Alcohols. Alcohols are known with OH. Okay, alcohols are known with OH. They could be numbered using the common name where you have methyl alcohol, ethyl alcohol, tertiary butyl alcohol. However, in the IUPAC nomenclature, the suffix OL replaces the E ending of every alkane, so that in methane, the E ending, when it becomes alcohol, you now have methanol. That is it. You see, methanol. This OL, if you replace it with E, you get methane. So this is ethanol, propan-1-ol. Because if this is this place, you have propan-2-ol. Then let us look at this one that looks a little complex. First of all, let us identify the longest carbon chain. And the longest carbon chain must give the functional group list number. So we have 1, 2, 3, 4, 5. And then you see that the OH is at position 2. So this will be pentan-2-ol. Chloro group, we have chloro group and methyl group at position 3. Okay. So the correct name for this compound is 2-chloro-3-methyl pentan-2-ol, not 3-methyl-2-chloro. No, alphabetical order naming. First of all, chloro comes before methyl. So even this name here is wrong. So it should be 2-chloro, 3-methyl, pentan-2-ol. Then we have esters. Ethers. Ethers is ETH, not EHT. Then we have ethers. So ethers in the IUPAC system, ethers are named as alkoxy-alkane. Alkoxy-alkane. Where, remember in ether you have two alkane groups. So you look at this one, there is an alkane here, there is another alkane. The longest chain is the parent, while this shorter chain is the alkoxy. So that is to say that the name of this compound is methoxy-ethane. Methoxy, because this is from methane, so that is it, methoxy-methane. Ethane. Then for this compound here, we have 1, 2, and then we have 1, 2, 3. So the longest is this 3, and then on this longest, there is a methyl group at position 2. So this compound will be ethoxy, because these are 2 carbons, ethoxy 2-methyl pentane, propane. Then we have the aldehydes. Aldehyde have carbon to oxygen double bond and the hydrogen attached. And aldehydes, we have the E ending of alkane replaced with Al. So that methane is now methanol. And then, because in aldehyde, the functional group is always at position 1. So there is no point mentioning the position of the functional group in aldehyde. However, when it is time to number for substituents, this numbering must start from the functional group. So we have 1, 2, 3, 4, 3,3-dimethyl butanol. The same thing goes for ketones. The same thing goes for ketones, where we have R2C double bond O. The functional group is this carbon to oxygen double bond surrounded by 2 alkyl groups. Just as we have in alkanal or aldehydes, the E ending of alkane So as I was saying, so the position here becomes very, very important. Carboxylic acid. So these structures are already the same thing here. I just wanted to show the structure so that we'll be able to identify them. Formic acid is a common name. The IUPAC name is methanoic acid. Acetic acid, the IUPAC is ethanoic acid. Lactic acid, the IUPAC is 2-hydroxypropanoic acid. Oxalic acid, the IUPAC is ethane-dioic acid. Acrylic acid, the IUPAC is propanoic acid, and so on. So this is stearic acid. The IUPAC name for stearic acid is octadecanoic acid. Octadecanoic already shows you that there are 18 carbon atoms. Tartaric acid, you have tartaric acid at 2,3-dihydroxybutane-dioic acid. Adipic acid as hexane-dioic acid. Acrylic acid, already we mentioned that. So this is just the structures of what are here in the table. Amines. There are two systems of naming an amine. We can name it as an alkylamine, or we can also name it as an alkanamine. So both of them have been accepted by IUPAC, so that if you have an amine, you can say methylamine or methanamine. Both of them are both acceptable. So you have the simplest amine here, methylamine, that is using alkylamine nomenclature, or methanamine using alkanamine nomenclature. Then you see this one, the amine, the position 1 is assigned to the carbon where the amine is attached, just like in alcohol. The position is assigned to the carbon where the amine, nitrogen, is attached. And so that will help us to be able to account for the substituents. So you can see here we have 1, 2, 3, 4. That means this is butyl amine. And then there is a methyl group at position 1. Okay. To continue that of amine, primary diamines are named by using the suffix diamine. Then triamines and so on. So if you look at this, you have 1, 2, 3, 4, 5. That means it's going to be a pentane. Then we see that there are amines, amino groups at position 1 and 2. And therefore, this is 1,2-pentane diamine. Okay? And then we also have this one, 1, 2, 3, 4. You see the amines at position 1 and 4, and that gives us 1,4-butane diamine, and so on. Exercise. I want us to quickly, very quickly at it, look at these compounds and see if we can get the names. We want to introduce polyfunction because we didn't discuss it yet. So you see here we have two functional update is the parent of the functional group. So OH is usually stronger. The OH is given preference, okay? And why this one is now named as a substituent. So with the numbering, we start from this carbon and not this carbon. So we have 1, 2, 3, 4, 5, okay? And then that is a pentanol, pentan-1-ol, because the OH is at position 1. Pentan-1-ol. However, there is a double bond, carbon to carbon double bond at position 4. Therefore, the correct name, the complete name is pentan, pent 4 in 1-ol. Pent 4 in 1-ol. Pent 4 to show that there are 4 carbon, 5 pens to show there are 5 carbon, 4 in to show that there is a double bond at position 1. Then we move to this one, which is an aldehyde and alcohol. So aldehydes are stronger than alcohol. So the numbering starts from the aldehyde 1, 2, 3, 4. So this compound becomes, remember we mentioned the aldehyde, okay, because they usually occupy position 1. Therefore, we now say this is a butanol, and then it has a hydroxy group at position 4. So this is a butan 4-hydroxy butanol. 4-hydroxy butanol. Okay, that's so far so good. I want to take your questions and contribution, questions, confusions, and questions. Time to clear confusion. Hello, are we together? Are we together? Aji, John. Any question? Any question?
No, sir. No, sir. No, sir.
Okay, no question. Okay.
Yes, sir.
Damilola. Damilola, any question? Somebody logged in with iPhone. That is not your name now. So who are you? Do you have any question?
No, sir.
No question.
Yes, sir.
Okay. Okay, Damilola says no. Inform. Eibio.
Sir,
Eibio, any question?
no,
No question.
no, there's a question, sir. In regards to the
Okay,
number 3, I didn't
go
quite
on.
understand.
Eh?
I didn't quite understand the number 3 naming.
The number 3 rule number
Yes, sir.
3.
Rule number 3.
Okay, we'll go to that, no problem. Any other question? Let us look at rule number 3. Rule number 3 says the parent carbon chain must be numbered in such a way that the substituent gets the lowest possible number. Lowest. So when you number, when you have identified the substituent, the correct numbering must be such that the substituent will get least. Two examples to show. We have identified the parent carbon to be 7. You can see 7. Both of them are 7. If you go from here, it's 7. If you go from here, it's still 7. Now, if we number from here, this methyl group, which is not part of the parent, which we are now treating as a substituent, this methyl group will be at position 4, while the second methyl group will be at position 5. 4 plus 5 will give us a total of 9. Okay?
Yes, sir.
Now, if we number from here, this methyl group will be at position 3. The second methyl group will be at position 4. 3 plus 4 will give us a total of 7. 7 is lower than 9. Therefore, if for any reason you were asked to name this compound, okay, and you choose to number this way, such that your own name is now 4,5-dimethyl heptane. That is totally wrong. It is totally which is to give the least numbering to the substituents. Because if you had considered it, the name of this compound would have been 3,4-dimethyl heptane. Because 3,4 is lower than 4,5. Is that okay now?
Yes, sir.
All right.
Thank you very much, sir.
Okay. You said?
I I said thank you very much, sir, for the clarification.
Okay, you are welcome.
Thank you.
So we meet next week by God's grace, the same time. All right, catch you. So in the next few hours, go back to the course page and you'll be able to download you get the passcode for the video. You'll be able to download that from the course page. So you can listen over and over and get yourself ready so that in the next facilitation, you'll be able to ask questions on things that you didn't get clearly while listening to this day's facilitation. If you go there, you still see the facilitation of other weeks. Try and assess them and get yourself prepared so that you have some questions during our live session. Thank you.